Last time we were talking about the electrostatic force and how it is much, much greater than the gravitational force. Let's talk about how much greater. First of all, let's do a physical example. We know that all bodies are essentially neutrally charged. You yourself have as many positive charges as you do negative charges, and a person who might be standing next to you would probably also be neutrally charged. So if you're asking why such an enormous force doesn't display itself more readily, in the case of people, we're both neutrally charged. Now, suppose, just for kicks, suppose each of you, the person next to you and you, had 1% more protons than electrons. What kind of repulsive force do you think would result from that? Do you think it would lift the Empire State Building? Oh, it would be bigger than that. Could it lift Mount Everest? It'd be bigger than that too. The repulsive force could lift the entire Earth. That's how enormous the electrostatic force is. Let's talk again about Coulomb's law and what results from it. So as we said last time, the Coulomb force is proportional to the product of the charge between two particles, 1 over the distance squared, times this constant, that's roughly about 9 times 10 to the 9 Newton meter squared per Coulomb squared. Of course, we've got to use those units to make sure that our force ends up in newtons. See some examples. We mentioned the charge of the electron. Charge of the proton is exactly the same, only opposite in terms of sign. And of course, the charge of the neutron is 0. It's a neutrally charged particle. Some questions might occur to you, and we'll touch on them just because they're sort of interesting. One might ask, well, protons and neutrons attract each other so much, how come they don't lie on top of one another instead of reasonably distanced as in atoms? And the answer to that is quantum mechanical. It's beyond the scope of this course, but it has to do with the Pauli exclusion principle. Another question that you might have thought of is, take a uranium nucleus. A uranium nucleus has 92 protons in it in a very small space. Wouldn't you think that those 92 protons would repel one another and the nucleus would fly apart? Well, the answer is, of course, it doesn't. And the reason that it doesn't is, in nature, there's something called the strong nuclear force that binds the nucleons in a nucleus together. The nuclear force is about 100 times stronger than the electrostatic force, but the nuclear force only acts under very, very, very short distances. But that's what holds this positively charged nucleus together. Of course, someone also once asked the question, how come electrons themselves don't fly apart since all they're made of is negative material? That's a really good question, but nobody's ever come up with an answer to it. The interesting thing, at least for our purposes, where Coulomb's law is concerned, is how do we do electrostatic problems with it? And to do that, we have to take advantage of the vector nature of electric forces. So, as you can see in the way we stated in the equation, we have this unit vector, R12, that is the line between the two charged particles. If the charges are positive, the force will push this charge this way and this charge this way. If one charge were negative, it would be attracted to the other charge. And we can take advantage of the vector nature to understand how systems of charges would work. So for example, first thing we might say is electrical forces obey Newton's third law. So the force of one charge on the other is equal and opposite to the charge of the second on the first. No surprise that Newton's third law continues to be obeyed. But we can also talk about the fact that in this case we have signs of charges. So if these two charges are opposite, you're going to have a force that is attractive in both cases. If this sign were positive, of course, this would be a repulsive force. If I have multiple charges, then the resultant force is going to be a vector sum of the forces. Let's say if I have 4 charges, it's going to be the force on each of the charges due to the others. And we can do some nice examples of how that might work in using Coulomb's law. Let's do a great example. Suppose I have 3-point charges in the following configuration. So I've got 3-point charges, 2.5 microcoulombs, 2.5 microcoulombs, and 3 microcoulombs, Q1, Q2, and Q3. And I want to find the electrostatic force on Q3 due to Q1 and Q2. We're going to employ Coulomb's law. We're going to break the forces into components because it's a vector quantity. So this is going to remind you of problems that you might have done with velocities, momenta, or even accelerations in your earlier physics class. And we'll do it in the following way. There are a number of methods one can use. I like this method the best because it seems to be the most foolproof. First off, we're going to find the components of the forces on Q3. So let's look at the force in the x direction, Q1 and Q3. I know that this is going to be a repulsive force, so Q1 is going to have a force that pushes down in this direction for Q3. That means the x component of that force will be in the positive x direction. The y component of that force will be in the negative y direction, you see? And so what I'm going to do, I'm not going to worry about the signs of the forces yet until I've gotten all the components together. So for F13x, that's going to be equal to, in this case, 9 times 10 to the 9 Newton meters squared per Coulomb squared times 2.5 times 10 to the minus 6 Coulomb, that's a microcoulomb, times 3 times 10 to the minus 6 coulombs, divided by the distance between them. Well, if this is 0.4 meters, that's 0.3 meters. Of course, it's the 3, 4, 5 triangle, so that has to be 0.5 meters. Then I've got to square that. 0.5 meters, I square that. And I multiply by the 4x, the cosine of this angle. Well, the cosine of this angle is, of course, the adjacent over the hypotenuse, so it's going to be multiplying 0.4 over 0.5. When I put all that together, F13x is going to be equal to 0.216 newtons. Similarly, if I want to find F13y, I set up the same equation and I multiply by the sine of this angle, which is the opposite over the hypotenuse, or 0.3 over 0.5. And that gives me F13y, turns out to be minus 0.162 newtons. Remember, we said that the force is pointing in the negative y direction, so it's minus 0.162 newtons. Finally, I can look at the force of Q2 on Q3, and notice there's something immediately that I see. Because these two charges are the same, the magnitude of F13y and F23y and F23x will be the same as the magnitudes of F13x and F13y. Because those charges are the same, Coulomb's law will say everything is the same except the direction of F23 in the y direction. Because that's going to be a positive charge. So F23y will be equal to positive 0.162 newtons. That means when I add the two components, F23y and F13y, Fy, which is the sum of those, Fy will be equal to F23y plus F13y. If I add them, that's 0. Through symmetry, the y component of the force on Q3 is 0. So the only component that survives is the x component. I know that in general, when I want to find the magnitude of the force on F3, on Q3, that's equal to the square root of Fx squared plus Fy squared. Fy squared, as we said, the sum of those y forces is 0. So all that I have is Fx squared. And of course, that's going to give me Fx in both cases is 0.216 newtons. So if I add them up together, F13x plus F23x gives me 0.432 newtons. Take this is 0.432 squared. This is 0, so the total force on F3 then is going to be equal to the magnitude of the force is going to be 0.432 newtons. Now suppose I want to find the direction of the force, which I always want to do. Well, in this case, of course, the way we do direction is to say the angle arctan of Fy over Fx is equal to, we'll call it phi, the angle at which the force is applied. And of course, since Fy is equal to 0, we can say then that this angle is 0. So phi is equal to 0 degrees. In other words, the force is along the x-axis. That's a fairly simple example of how to use superposition to find the force on one charge due to a group of other point charges. Another nice example, let's compute the ratio of the electrostatic force to the gravitational force between a proton and an electron. Okay? Well, the gravitational force between a proton and electron is mass of the electron, 10 to the minus 31 kilograms, 1.67 times 10 to the minus 27 kilograms for the mass, so it's mass of the electron, mass of the proton. I've got to multiply that by the gravitational constant, 6.67 times 10 to the minus 11 Newton meters squared per kilogram squared. That's big G. Divide by the distance squared. And by the way, I'm not going to worry about the distance between the proton and the electron. Why? Because in each case, the distance will be the same. So for the electrostatic force, I'm going to say, well, it's 9 times 10 to the 9 Newton meters squared per Coulomb squared. The charge of the proton and charge of electron, 1.6 times 10 to the minus 19 coulombs each. So I square that. If I take the ratio, this is also over r squared. And of course, if I take the ratio Fe to Fg, the r squareds are going to cancel out. And what I'm going to get as a ratio is going to be Fe over Fg is equal to 2.3 times 10 to the 39th. That's an enormous, enormous number. That gives you an indication of how strong the electrostatic force is compared to the gravitational force. Let's do some other examples. So here's a nice example. Suppose I have two charges separated by a distance of 2 meters, and let's say they're both positive charges. The question is, where would I insert a negative charge between those charges such that the net force on that negative charge would be 0? Okay? So somewhere in between I can put and it could be a positive charge as well, it doesn't really matter. So that's the case. Let's do it for instance. Let's suppose that the positive charge that lies on the x-axis has a value of 6 microcoulombs. So we'll call that Q2 is equal to 6 microcoulombs. Let's say that Q1, the charge that lies 2 meters away from there, has a charge of 15 microcoulombs. And we want to find the location in between the two where the force on a negatively charged object would be 0, the net force. Well, the way to do that is to say it must be that, for that to be the case, we'll call this other charge Q3. We don't need to know the size of it, as it turns out. We need to say that the charge of object 1 on object 3 must be equal to the size of the charge of object 2 on object 3. F13 I can write as 1 over 4 pi epsilon naught. We'll start with the one with the origin, start with the 15, so that's 15 times 10 to the minus 6 coulombs times Q3 divided by, we'll call that distance r squared. Let's call that, you know what, let's call that distance 2 minus r squared. Let's call F23 1 over 4 pi epsilon naught 6 times 10 to the minus 6 coulombs times Q3 divided by r squared. Right? If the location of the charge is at some distance r with respect to Q2, then it must be at some distance 2 meters minus r with respect to Q1. These two forces have got to be equal in order for the net force on Q3 to be 0. So I set this expression equal to each other, and notice what I'm going to get. I'm going to have to cross multiply, and I'm going to get a quadratic. So when I do that, I'm going to get 4 minus 4r plus r squared times 6 times 10 to the minus 6 is equal to 15 times 10 to the minus 6 times r squared. In order to solve this, I've got to use the quadratic formula. And what I will get, remember the quadratic formula says, in this case, r is equal to the square root of b squared minus 4ac over 2a, where it turns out that when I multiply all this out, a will be equal to 9, b will be equal to 24, and c will be equal to 6. I solve this, and I will find that r is equal to 0.775 meters to the right of Q2. Okay, so that will make if I put that third charge 0.775 meters away from Q2, away from the origin, the net charge on, the net force on Q3 will be 0. That's a nice example of electrostatics. We'll do one more. This is another one. This will recall some of what you learned in your first physics course, 201 or whatever first course you took. Suppose we have the following situation. Suppose I have two charged spheres in equilibrium. Let's say that they're separated by a distance 2a, and what is keeping them in equilibrium is the electrostatic repulsive force between the two charges, and then of course the tension in the strings. What we'd like to find from this, suppose we're given the mass of the spheres and the length of the string, and also the angle between the string and the vertical. Let's find the charge on each of these identically charged spheres. It's an interesting problem, and it will remind us that we need a free body diagram. So because the spheres are in equilibrium, I know that the sum of the forces in the x direction and the sum of the forces in the y direction have got to be 0. Free body diagram tells me that if I let's just look at the charge on the right. Let's look at the charge on the right. I have a force of gravity that pulls downward. I have a force of electrostatic repulsion from the other charge that pushes it to the right. And I have a tension force in the y direction that balances the force of gravity. I have a tension force in the negative x direction that balances the electrostatic force. So those four forces have to work in conjunction with one another, and that will enable me to calculate the charge of each of those spheres, just by even examining one. So first off, I'm going to say, well, I know that I can get the length, the distance between the two charges, 2a. If I find a first using trigonometry, I can say that a is equal to L sine theta. Theta is 5 degrees, let's say. And let's say that L is 0.15 meters. So if I do that, I can find that A is equal to 0.013 meters. That means the two spheres are separated by 0.026 meters because they are separated by a distance 2a. Let's look at the forces in the y direction. I can write with respect to angle theta, the tension in the y direction, I can write as T times the cosine of theta. Notice y corresponds to cosine and not sine in this case. Tx would be T sine theta with respect to that angle. T cosine theta would have to be equal to mg, the force of gravity in the y direction. T sine theta for the x direction would be equal to the electrostatic force between those two charges, which I can write as 1 over 4 pi epsilon naught q squared, each charge, divided by the distance between them squared, 0.026 meters squared. So I have two equations and two unknowns. The easiest thing to do is to say, well, let's take the first equation. I can write T as equal to mg divided by cosine theta, and I can insert that into this expression, where I can say then T is now mg sine theta over cosine theta is equal to 1 over 4 pi epsilon naught q squared over 0.026 meters squared. That becomes mg tan theta. So if I put in my values, if I put in 5 degrees here, the mass is 0.03 kilograms here, g is 9.8 meters per second squared here, I have everything except q. So all I have to do is, and this of course is equal to 9 times 10 to the 9 Newton meters squared or Coulomb squared. If I put all my numbers in and solve for q, I will end up with q is 4.4 times 10 to the minus 8 coulombs.
20 seconds, Dr. Blows.
Beautiful example of electrostatics. We'll talk about this more in our next session.